Okay, so this chart, you will see that we have the electronic structure, which is the families, and then you have the geometry, the actual shape of it. The next line says the areas of electron density. So how many areas are there electrons around the central atom? Then you have your number of bonded atoms, bonded areas, and then you have your number of lone pair electrons. And then you have your angles, and then the polarity. Again, the polarity will be based on, we're assuming that it's all the same atom on the central atom. And then you have a couple of asterisks down there at the bottom, and we're going to talk about that. And then hybridization, which will be Thursday's topic. I am actually going to just go through the shapes first, and then give you time to come back and fill this out, rather than me filling it out and then going over the shapes. We're going to look at the shapes, fill it out as we go along. Okay, so the very first one we have, our simplest shape here. I am going to list the family, the geometry, the angles, and polarity. Where are you at? There you go. Okay, so the very first one, our simplest one, is the family is linear. To further classify it, the shape is linear. So we have two areas of electron density here. And the angle, bond angle, is 180 degrees. So if we're going to look at this and we're saying they're both the same atom hooked up to this, then the polarity on this would be non-polar. Questions? Good? All right. So the next family that we're going to take a look at is the trigonal planar. So we have the trigonal planar family, and we have two types of geometry in this family. The first one is named right after its family. It is trigonal planar. If you look at those bond angles, that is 120 degrees between each molecule. If they're all the same molecule, then the polarity would be nonpolar. Okay, so if we were to remove one of those atoms, and now we have two atoms on it and one lone pair, this becomes trigonal planar, further classified for geometry as bent. The angle right in here is less than 120 degrees. Okay, so when we get that lone pair, we have that geometry, and it's pushing down on that those two atoms, and it pushes that angle and makes it smaller than what it was when we had the three atoms on there. So it's about 117, but less than 120 is good. Okay, they're not going to ask you for the exact angle. Again, you have the lone pairs there, so my polarity would be polar. Okay? Okay, so our next family that we're going to look at is trigonal bipyramidal. Oh, sorry, no, not, oh my gosh, I skipped one. Not trigonal bipyramidal. Tetrahedral. Skipped ahead. So this whole family is tetrahedral, and there are three different types of geometries in it. The very first one is named after its family, and it is tetrahedral. Between each area, there is 109.5 degrees. 109.5 degrees. And since these are all the same atom on it, we are saying it is non-polar. It is tetrahedral family, tetrahedral geometry. Okay, because we have the 4 on there. Now, if we remove one of those central atoms, what happens is now we've got a lone pair. The angle between these atoms is going to become smaller because of that lone pair, and this is going to be less than 109.5 degrees. And we call this one trigonal pyramidal. And the polarity would be polar. So then the next one in the tetrahedral family is we've lost 2 of these electron or these bonds. So now we have 2 lone pair of electrons. The polarity gets even, the angle gets even smaller. So this is less than 109.5. This is bent. This is our water. And the polarity is polar.
So it can be bent regardless of how long.
Yes. Exactly. Okay. The next family is trigonal bipyramidal. And the very first one in its family is named after it. And if you can see, we have this pyramid, and it is it's 2 pyramids on top of each other. That's where it comes from, the bipyramidal. So the first one is trigonal bipyramidal. I'm spelling bipyramidal wrong. The angles here are going to be, no matter which way we look, it is going to be 90 degrees. So we have 90 degree angles. So 90 degree here, here. And 120. 90 degree. If you're looking between, let me see. This area right here, between this one and this one and this one and these, okay? So that is a 90 degree angle. But then you have these 3 that are in the middle, and those are 120. So it's a 90 and 120. And the polarity is nonpolar. So now what we're going to do is we have that structure, the two that are straight away from each other, and then we have the three that are 120. We're going to remove one of those three at the 120, and we get this molecule here. We call this the seesaw, because it kind of looks like a seesaw or a teeter-totter. Our angles get smaller, so this is going to be less than 90 and less than 120. And because of those lone pairs, it is polar. Huh? The geometry is the seesaw. So it's trigonal bipyramidal seesaw. The next one, now if we pull off the second one of those, what we get is we have two lone pairs up here on top. This is very, what do you call that? A very unique name. It is T-shaped.
T-shirt.
Our angles now between here and here are going to be less than 90 degrees. And again, it's polar. The next one, now we've removed, and we have all three of those ones that were giving us our 120 degree angles. Those are all removed, which means we have three lone pairs. This is trigonal bipyramidal, and this is linear. The angle is now 180 degrees, because while we have these lone pairs up here at top that are pushing down, we also have these lone pairs over here that are pushing up, and so it makes a 180 degree angle. And this is one of your exceptions. While it has lone pairs on it, it is nonpolar. Non-polar, one of your exceptions.
So this would be, like
No, this would be more like that iodine we drew yesterday. The iodine, the I3 with the negative charge. Okay. Next. Oh, I'll go back. Everybody good?
Are we doing hybridization yet?
We're going to do hybridization on Thursday. I'm not lecturing tomorrow. Tomorrow will be POGL. And then Thursday.
Okay.
Okay, next. Our last family is our last family is the octahedral. When you hear the word octa, what do you think of? 8. Now, this does not mean 8. This is octahedral. There's 8 sides, but it has 6 bonds to it, okay? So it has 8 sides, but there's 6 bonds on it. So our first one in the octahedral family is the octahedral. Every angle is 90 degrees. Every angle, no matter which way you turn it, you're going to have a 90-degree angle. And this would be non-polar. So the next thing I want to do, if I pull off one of those atoms and now I have a lone pair, what happens is this becomes what we call square pyramidal. Okay, so those outer ones are making a nice little square, but we also have a pyramid. Our angles get smaller, so it's less than 90 degrees, and we have the lone pair, so it is polar.
Why do they all get small?
Because those lone pairs start pushing, they're stronger, and so they're pushing them up, yes, depending on where the lone pairs are. The next one, let's remove another atom, and now we've got two sets of lone pairs. We are no longer pyramidal. We are going to be square, planar. This goes back to being 90 degrees. And this is one of those ones where it is non-polar, even though it has those lone pair electrons, because they're kind of counteracting each other. That is one of the biggest mistakes I've seen is you'll get the family versus the geometry messed up. So remember those four families, or four families. 5 families. 5 families, and then the geometry shapes. And then the angles. So let's go do a couple of these questions, and then we'll be done. Everybody good with this? Okay. A molecule, true or false? A molecule that has polar bonds will always be polar. False. Give me an example.
Carbon dioxide.
False. Okay, carbon dioxide has polar bonds, but it's non-polar. Carbon tetrachloride, polar bonds, but it's a non-polar molecule. Draw those?
Oh, yeah.
Just like you did.
Thank you.
So you have it being pushed out that way, pushed out that way. For carbon tetrachloride, again, this time it is being pulled out. But the overall molecule is non-polar. All right. Next example. True or false? Lone pairs make up a polar molecule. Oh, make a molecule polar. False. Give me an example. Square planar. What else do we have?
I3 negative.
I3 negative, so it's linear, but it is trigonal bipyramidal. Questions on that? Okay. The next one, I think I put a slide in there a couple of times, so you can just cross out that next slide. Draw the Lewis structure for carbon dioxide, and we just did that. And the question says, does it contain polar bonds? Yes. Is it overall polar or nonpolar? Nonpolar. Yes. So the poles cancel out. We have the same, it's symmetrical. So because it's symmetrical, we'll have that. It'll be nonpolar. Questions on that? So being able to recognize these, your test is like 20-something multiple choice. It's a lot of multiple choice. Being able to know the families and all that stuff. There is some free response, but they'll be short free response. Huh? Yeah, xenon, yes. All right, so let's draw the next one. The Lewis structure for xenon tetrafluoride. So probably need to go to the needed, available, shared. We have 5 of them. They each want 8, so 40 available. We have 4 with 21 and 1 with 8. Oh, not 21. 4 with 7. 28 plus an 8. 36. So we're sharing 4 divided by 2 tells me we have 2 bonds, but we have 4 atoms, so we know that this is probably going to be expanded octet. And then we finish out the fluorines. So we have 32, 33, 34, 35, 36. So now I want to know family, geometry, polarity. There's 6 on it. So if it's 6, it has to be family of octahedral. Square planar. What's the polarity? Nonpolar. So this is one of the ones where we have lone pairs, but it is nonpolar. Very good. Do you want me to draw these next examples with you? Or you can do them? SO3. Needed, available, shared. We have 4 of them. Each of them needs 8, so that's a total of 32. We have 4 that have 6 each, 24. So we share 8. So we'll have 4 bonds. So we have sulfur, our oxygens. One of them needs a double bond. So we have 2, 4, 6, 8. 18 and 4. So my thing says it wants to know the molecular geometry, the bond angle, and polarity. So what is the geometry on this? Pyramidal? There's no lone pair, so it's trigonal, planar. While there is that one double bond, that double bond's going to be moving, so that makes it end up being nonpolar. And the angles in trigonoplanar are 120 degrees.
Do you decide the shape and family based off of bonds or how many individual things there are?
You base the family on the number of electron areas. So there's 3 electron areas, so that makes it trigonoplanar, and then you base the geometry on how many bonds it has. So since there's 3 bonded. Okay, the next one, SO3. So this time we've added 2 electrons. So our needed is 32. Our available is 26. So shared is 6 divided by 2, so 3 bonds. So now I don't have the double bond. I finish out my oxygens, and I have 2 left over, and they go on the central atom. And it makes it trigonopyramidal. The polarity is trigonopyramidal, but that's within the tetrahedral. So it's tetrahedral family, geometry is trigonopyramidal. And it is polar. And the angle is less than 109.5. Everybody good? I'm going to draw one more. I'm going to draw the I3. We already did that yesterday, so I'm going to just redraw it. What it looked like yesterday, so we can give it its shape and polarity. So something like that. What's its shape, or what's the geometry on it? There's 6 areas of 6. Wait, 5. 1, 2, 3, 5. It's trigonopyramidal, so it's linear trigonopyramidal. It's nonpolar, and the angle is 180. Okay, so try drawing that ICl3 and tell me what you get on there. Other than that, is there any homework tonight? VSEPR, yes, D.
Yes.
Homework is D.